Hi friends, this is PH 4501, lattice vibration and thermal property. Among that, in the case of thermal property, we are covering 2 points in the thermal property for solid state material. One is a specific heat and the second one is a thermal expansion. Let's begin with the thermal property, specific heat. In the previous lecture, we have discussed about the specific heat and its classical theory, which is well known and very first theory referred as Dulong and Petit law. The Dulong and Petit law was suggesting that only the specific heat of each and every material is about to be constant, and that is always 3R or 3 Nk, and that is how they are true, but not always, because either the model will be only supportive near to the melting point of the material, which is always 3R constant, or it is also getting fail, especially in the lighter case elements of a periodic table like beryllium, boron, carbon, etc. So to upgrade this one, in beginning of the 19th century, somewhere in the 1907, Einstein has given a theory, and that is very widely popular and almost true uh, for almost continuous and widely used by scientific society for almost 5 to 7 years, and later on this theory also get upgraded by scientist Gadhvi in somewhere in 1913 1913, and that is referred as a Gadhvi theory, and till the date Gadhvi theory is still giving a almost correct speculation for the supportive to the empirical data. And this particular entire scenario is started in support to the classical theory, but Einstein has introduced the quantum concept, and he has introduced the almost similar kind of the assumption which was put forward by the Dulong and Petit in his classical theory. So rather than taking 1 kg material for rising up the temperature of a 1 Kelvin or a 1 centigrade degree, always molecular specific heat is advisable. In a molecular specific heat, we do have two varieties, as we are aware in 11th and 12th grade, that is Cp and Cv. Cp, that is a specific heat at a constant pressure, and Cv, that is a specific heat at a constant volume. But out of these two, it is always advisable and practically it is easy to measure the Cv rather than the Cp, and therefore it is always practical approach to be accepted, and all model has developed on the basis of Cv, that is a specific heat at a constant volume. Einstein has also considered some around n number of atoms, so he has taken the about 1 kilomole substance, and therefore there is a one available number of atoms in this particular solid system would be around equivalent of a 1 Avogadro number, that is a Na, and each and every atom which is showing the simple harmonic motion, and therefore there is a, you can say that n number of atomic harmonic oscillators are available. Now in a solid there is a 3 degree of freedom along the x-axis, along the y-axis, and along the z-axis. So simple harmonic motion could be possible along the x-axis, along the y-axis and along the z-axis. So a one atom is able to represent three simple harmonic motions along the x, along the y and along the z-axis. And therefore a single atomic harmonic oscillator or atomic oscillator is representing basically a three simple harmonic motions, and therefore it is represented as a three entity of a three atomic harmonic oscillators. तो कुल मिला के अगर n नंबर ऑफ एटम्स है तो टोटल एटमिक हार्मोनिक ऑसिलेटर्स हो जाएंगे 3Na, and that's why it's written it's a 3Na. And very important point, it is written here, and that is the atomic harmonic oscillator, and which is independent atomic harmonic oscillators. You can read it out here, 3Na independent. That means एक एटम में वाइब्रेट अगर कर रहा है x फ्रीक्वेंसी पे, तो उसके बगल वाला एटम के साथ उसका कुछ लेना देना नहीं है, ऐसा आइंस्टाइन ने एज्यूम किया. रादर दैट वाज आल्सो एज्यूम्ड बाय द ड्यूलोंग एंड पेटिट. सो दैट मीन्स द स्प्रिंग बॉल मॉडल जो वहाँ पे आज अभी तक हमने विजुअलाइज किया, वो स्प्रिंग बॉल मॉडल तो विजुअलाइज हो रहा है क्योंकि वन एटम इज वाइब्रेटिंग, देन द एडजॉइनिंग एटम इज ऑल्सो वाइब्रेटिंग. But still, for ease of mathematical and in support of the classical concept and newly introduced to the quantum concept, they are still stick to the same idea that all atoms are having a freedom to do that independent vibrations. But for because they are of a solid crystalline material and they are of the same type of the atomic structured atom entity, and therefore it was as per the equipartition theorem concept, Einstein has assumed that they are doing vibrations at the same frequency. So they do have a independent harmonic oscillators. तो टोटल एटमिक हार्मोनिक ऑसिलेटर्स हो गए 3Na. इसका रीज़न मैंने आपको बताया कि द रीज़न इज़ देयर इज़ अ 3 डिग्री ऑफ फ्रीडम्स, एंड अगर टोटल Na नंबर ऑफ एटम्स इज़ अवेलेबल, then there is a Na number of atomic harmonic oscillators are available. Since one atom is representing a 3 simple harmonic motions, so I can say that there is a 3Na independent harmonic oscillators are available. Or each and every one are vibrating with the same frequency, and let us assume that that is a nu. With this third assumption, पहला assumption Na number of atomic harmonic oscillators, दूसरा number 3 degree of freedom, so 3Na harmonic oscillators, plus they are the independent harmonic oscillator. That means one is not directly or indirectly connected to their adjacent atoms, and therefore the independent harmonic oscillators. And the third assumption is they are having the same frequency, that is a nu. So with this three particular postulates, or you can say the prerequisite condition for the Einstein model, he begins to derive the model for the specific heat at a constant volume. The half kinetic and the half potential. The meaning of the questions is that only a certain discrete value of the energy are allowed. So this is how the Einstein has introduced the quantum concept rather than the classical model of the base of the model of your ड्यूलोंग-पेटिट लॉ. तो ड्यूलोंग-पेटिट लॉ की जो नींव है वो क्लासिकल थियरी थी. तो यहाँ पे आइंस्टाइन ने ऐसा सोचा कि हाफ काइनेटिक और हाफ पोटेंशियल एनर्जी, एंड दैट वुड बी द मीनिंग ऑफ अ क्वांटाइजेशन इन द only a certain discrete value of the energy are allowed. Whereas the classical concept says that the any range of the energy can be absorbed by the oscillators. अगर आपको याद है तो लास्ट टाइम के लेक्चर में मैंने बताया था द एटॉमिक हार्मोनिक ऑसिलेटर कैन कंज्यूम और रिलीज द एनर्जी इन बिटवीन 0 to infinity. So classical mechanics is made up a mode of an oscillator can have the continuous range of the energy, whereas in the case of quantum concept they have the varieties of a not all the range of energy but the quantized range of energy. So ये एक दूसरा concept Einstein has introduced over here, and using the Planck's equations, he has given the energy associated to the atomic harmonic oscillators, and that is E is equal to h nu. And if there is a n number of E is equal to nh nu, or E is equal to n h cross omega. So omega is equal to 2 pi f or the 2 pi nu, and h cross is equal to h upon 2 pi. So 2 pi get cancelled, so it becomes the nh nu in only. So here this n is suffix over here, so that will define its the energy level. It's whether it's a ground state, then n will be the 0, so 0 will be having no energy. So here it is also interesting, the ground state will be represented by the digital number 1. So you have to exclude the n is equal to 0 integer. Anyway, so suppose you having a dn number of oscillators. So actually तो मेरे पास कितने oscillators थे, 3n है, but I am taking a very small regimes of the solid crystalline material. ये पूरे solid crystalline material में से मैं थोड़े से very small amount of the catchment I am taking a piece, and that is the region which covers, that regime is covered just dn number of oscillators. So that is how the Einstein has begun with this methodology to derive the mathematical model for the specific heat. And if there is a dn number of oscillators which is lies in between the range of the energy in between E to E plus dE, माने dn number of, ऐसा एज्यूम कर रहे हैं कि dn नंबर ऑफ ऑसिलेटर्स कहाँ पे पड़े हैं, तो कि E से लेके E प्लस डी एनर्जी. फिर से याद दिलाऊं कि यहाँ पे ये ऑलरेडी आइंस्टाइन ने बताया है एजम्पशन में कि दे हैविंग अ डिस्क्रीट एनर्जी वैल्यूज़. तो ये डिस्क्रीट एनर्जी वैल्यू वाला ही कंसेप्ट इज काइंड ऑफ अ क्वांटम कंसेप्ट. ठीक है, तो माने हर कोई एटॉमिक ऑसिलेटर या तो एटॉमिक हार्मोनिक ऑसिलेटर की एनर्जी सेम है, ये कंसेप्ट नहीं है, बट दे हैविंग अ डिस्क्रीट एनर्जी लेवल. सेकेंड पोस्टुलेट उसने बताया था कि देर इज़ अ 3 डिग्री ऑफ फ्रीडम, सो देर इज़ अ 3 n नंबर ऑफ ऑसिलेटर्स आर देयर, बट दे आर वाइब्रेटिंग विद द सेम फ्रीक्वेंसी. ठीक है, ओके. सो देयर मीन एनर्जी कैन बी पुट इट इन द शेप ऑफ इक्वेशन एज मीन एनर्जी इज शोन बाय अ बार, और या तो कभी कभी कैरेट की साइन भी आती है, राइट. सो ई कैरेट या तो ई बार इज गिवन बाय अ समेशन ऑफ एनर्जी मल्टीप्लाई बाय द अवेलेबल नंबर ऑफ ऑसिलेटर्स. अगर मेरे पास डी एन नंबर ऑफ ऑसिलेटर्स है और हर किसी ऑसिलेटर्स की एनर्जी ई है, rather e to let's say e plus de, and de is very futile, so I can say on an average it's the average energy E. So E into dn divided by the total number of available oscillators और उसका समेशन किया, तो डिवाइड बाय द समेशन ऑफ dn. सो ये मुझे एवरेज एनर्जी देगा. सो इक्वेशन 7.12 gives me the average energy. For a statistical mechanics, one knows that the number of oscillators is dn having the energy in between E to E plus dE, then at the temperature T it is proportional to exponential of minus E upon kT. This is basically derived from the Boltzmann's law of equipartition theorem. कि अगर ये बेसिकली लॉ जो था वो एक्चुअली gaseous molecules के लिए था. Within a confinement chamber, if you are providing a energy E to the molecules, then the each and every molecule will consume the same energy, which is directly exponentially inversely proportional to the E and sorry, directly exponentially proportional to the energy E and exponentially inversely proportional to the temperature T. So that is a e to the power minus e upon kt. So फिर से अगर मेरे डी dn नंबर ऑफ ऑसिलेटर्स है एंड दे आर लाइंग इन द एनर्जी रेंज ऑफ e to e plus de, then at the temperature of T, which is proportional to the exponential of minus e upon kt. So the statistical mechanics, one knows that the number of atomic oscillators dn, अगर मेरे पास dn नंबर के oscillators हैं और उसकी सभी की एनर्जी e to e plus de के बीच में आ रही है और at a temperature T, this number of oscillators will be proportional to exponential minus e upon kt. अगर ये है तो वी आर सब्स्टिट्यूटिंग E इज इक्वल टू E इंटू डी ए. फिर से मैं इक्वेशन आपको बता दूँ तो E इंटू डी एन, तो आपके पास डी एन पता चल गया कि डी एन कितना रहेगा मेरे पास. द डी एन नंबर ऑफ ऑसिलेटर्स विल बी प्रोपोर्शनल टू ई टू द पावर माइनस ई अपॉन के टी. सो यहाँ पे डी एन की वैल्यू की जगह ई टू द पावर माइनस ई अपॉन के टी आएगा और एनर्जी की जगह आएगा E इज इक्वल टू एन एच यू, या तो एन एच कट ओमेगा या तो एच क्रॉस ओमेगा, वॉट एवर द वे यू आर प्रोनाउंस. सो आई एम नॉट टेकिंग ओमेगा बट आई एम टेकिंग एन एच न्यू. सो एन एच न्यू that is represented the energy and the dn is always proportional to the e to the power minus e upon kt and E is equal to again nh nu. So E is replaced by minus nh nu upon kt. And same way total number of available oscillators, that is summation of exponential minus nh nu upon kt. So now this can be expand this series, then you will be having this term as well as you will be having this term. So start with the n is substituting with the 0, then substitutes n is equal to 0, so exponential with the 0, so that is e to the power 0, so that will be 0, but wait a minute, yeah, so e to the power 0, so that is equal to basically a 1, but that is when you multiply with the e factor, so that is n is here also, so that is 0, so the first term becomes 0 in the numerator, but the first term is available at the bottom. So the variations of the numerator and bottom is almost similar except the first digit. Now let us assume that x is equal to minus h nu upon kt, so the entire equation become in this shape, and this equation looks like basically the numerator is basically integration of d of dx log of the bottom or the denominators. So d by dx log of denominators is equal to this both numerator and the denominators terms. So this entire both square bracket can be written as the single square bracket. Okay, now with this we are simplifying the mathematical derivative on the above equation. Now this power series is truncated to the this series on basis of neglecting the higher order term. Okay, so by neglecting the higher order term, and you can having the relation like this. Then when the expanded series is truncated to the series like 1 over 1 minus e to the power x. Okay, so d by dx is expanded like this, and substitutes their value over here, then it's a h nu upon minus e to the power x upon 1 minus e to the power x, and that is resulted into the equation. And finally I having a equation like a average E is equal to h nu upon e, substitutes the value of x, then e to the power h nu upon kt minus 1. So this equation is basically the equation of a one atomic harmonic oscillator. याद रखिएगा कि एच न्यू अपॉन ई टू द पावर एच न्यू अपॉन के टी माइनस वन, दिस इज द एनर्जी एसोसिएटेड टू द सिंगल एटॉमिक हार्मोनिक ऑसिलेटर्स. तो मेरे पास तो टोटल 3n नंबर ऑफ एटॉमिक हार्मोनिक ऑसिलेटर्स है, सो आई शुड मल्टीप्लाई बाय 3 इंटू द एवरेज एटॉमिक हार्मोनिक ऑसिलेटर्स ऑफ द सेम. और मेरे पास टोटल कितने एटॉमिक हार्मोनिक ऑसिलेटर्स थे? 3n है, राइट. अब मैं बिगिनिंग में ही की. सो दैट इज U, that is the total energy associated to the crystalline system, is 3Na, that is the total number of atomic harmonic oscillator, multiplied by a single atomic harmonic oscillators, that is the average energy of that. So 3Na into E bar. He substitutes the value of E bar over here, so the equation is like this. And then you take the first derivative with respect to the temperature, that will define the specific heat. So your equation will be like this. Now h nu upon k, that is represented by theta E, which is known as the Einstein temperature. This is, I think you need to remember that Einstein temperature is represented by theta E, and their numerical value is equivalent of h nu upon k. अगर आप ध्यान से देखो तो this k will Boltzmann constants. So theta E is basically a constant. It's a Einstein temperature, but that is equivalent of h nu upon k. So if I substitute the that value over in the above equation, my specific heat relation will be in this shape. Okay. In further part, I substitute the value of the theta E over here. The shape of equation would be looks like this, and this entire part, the theta E upon t is as it is, and this part is remain almost constant and known as a Einstein function. So it's referred by f of capital E is also called the Einstein functions. E to the power x upon e to the power x minus 1 जो था, उसकी जगह e to the power theta E upon t upon e to the power theta E upon t minus 1. So Einstein functions of theta E upon t, that is your final equation of your Cv upon 3Ru, or Cv is equal to 3 Rydberg constant f of E theta E by t. Now within this you can visualize two special cases, and that special cases having a one relation where h nu is very much lesser than the kt. तो kt is a temperature or h nu is a product. So h nu product is very much lesser than the kt. So the h nu energy should be very much lesser than, so oscillating energy should be very much lesser than the thermal energy. या तो temperature is very high. So this is a case of a high temperature, right? And there would be one more is a low temperature. So high temperature, it is observed that it is very much similar to the Dulong-Petit law. So in a way Einstein theory is also supportive to the Dulong-Petit law, but that is for the high temperature range only. And even in the previous lecture we had discussed, the high temperature or the Dulong-Petit law is 100% correct, but at a close proximity to the melting temperature of the material. So anyway, so h nu upon e to the power x minus 1, where x is equal to h nu upon kt, if I will assume that, then the expansion series I can visualize like this. And if I will truncate it to the series to the first order only, then 1 plus x, because x is very small, because t is very high. If t is very high, then x is small, then higher order will be much smaller. The contribution to the power series with a higher power is negligible. So the series can be truncated to 1 plus x. So e to the power x replaced by 1 plus x, 1 get cancelled, so h nu upon x, and ultimately the equation become E is equal to kT. So this is exactly the replica of your Dulong-Petit law. So you can say that the higher temperature case in the Einstein model, it is exactly the supportive to the Dulong-Petit law or the classical approach, and that is almost true that near the melting temperature the specific heat is always constant, and that is equivalent to 3 times of the Rydberg constants or 3 Ru 3 Nk. Okay, and the second special case, that is at a lower temperature, and lower temperature, that means it is H nu should be greater than the kT. So if H nu upon kT is much greater than the 1, that means it is a low temperature case. Then the average energy will be given by H nu upon e to the power H nu minus kT, because if the t is very small, then this function is very high, then minus 1 to this part or not, it doesn't make any difference. जैसे कि 100 में से एक सब्ट्रैक्ट करो या ना करो, कोई फ़र्क नहीं पड़ता है, 1000 में से एक सब्ट्रैक्ट करो या ना करो. सो एक्सपोन ई टू द पावर माइनस एक्स माइनस 1 जो था, तो 1 हमने इसलिए निकाला क्योंकि बाई सब्ट्रैक्टिंग का 1 डजंट मेक टू मच चेंज इन द मैथमेटिकल वैल्यू. So mathematically you can say that this is almost equivalent to h nu upon e to the power h nu upon kt. Now again we know that we are taking a 1 kilomole material, and therefore there is a 3n number of the atomic harmonic oscillators do available. So we are multiplying a 3na into the average energy of a 1 atomic harmonic oscillators at a low temperature. ठीक है, एंड देयरफॉर यू कैन फाइनली डिड्यूस दिस रिलेशन. सो अल्टीमेटली डी यू बाई डी टी कर दिया तो आपको u मिल गया, तो फर्स्ट डेरिवेशन विद रिस्पेक्ट टू हाई टेम्परेचर कर लिया तो आपको ये मिल गया. एम आई क्लियर? सो सी वी इज इक्वल टू 3 Ru बाई एच न्यू अपॉन के टी होल रेज टू स्क्वायर एक्सपोनेंशियल माइनस एच न्यू बाई के टी. एंड हाउ इट लुक्स लाइक. तो यहाँ पे देखो कि द डॉट्स आर द एक्सपेरिमेंटल ऑब्जर्वेशन. तो एक्सपेरिमेंट 100 केल्विन से ऊपर ये आइंस्टाइन मॉडल इज़ वेरी मच मैचिंग विद द एक्सपेरिमेंटल मॉडल, और ये फ्लैटन पोर्शन जो आ रहा है दैट इज़ इक्विवेलेंट टू द 3 Ru और द क्लासिकल थियरी और द ड्यूलोंग-पेटिट लॉ. तो ये जो लोअर टेम्परेचर माने 100 के नीचे टेम्परेचर में अगर आप देखो केल्विन, 100 केल्विन से नीचे, then the Einstein model is decay faster than its actual experimental observation. तो यहाँ पे हम बोल सकते हैं कि Einstein model is not supportive to the lower than the 100 Kelvin, right? So 100 Kelvin के नीचे Einstein model supportive model नहीं था, because Einstein is decays with the square function, and ideally experimentally it is observed that the experimental data is decays with the cube function. Okay, so with this I am stopping here, and this is the syllabus of the CIA 2. All the best, do best in your exam, stay home, stay blessed and take care. Best wishes for the exam.